Let's see some of the other applications that we have of depth-first search. For example, pathfinding is a pretty common problem. We want to figure out how we can get from one vertex to another vertex. Now, assuming that there is such a path, we can find one just by slightly modifying our depth-first search algorithm. Now, before we get to that, I want to remark that we can already figure out yes or no, is there a path, without actually finding it, by also using our depth-first search algorithm. So for example, let's go back here. We could keep track of a new label for each vertex and label it based on which connected component it belongs to. So we could have, let's say, here's all the vertices belonging to connected component 1, here's all the vertices belonging to connected component 2 and 3, just by passing a new parameter. So let's say I have some integer c, which represents which connected component we're in. We can pass this along to our DFS calls so that every time we call DFS on a vertex, we set a new label on that vertex to be to basically indicate that V belongs to connected component C. Just some additional labeling scheme. And to use the same integer label for every other vertex which is reachable from that one. So then we could label each one of these vertices as this belongs to connected component 1, and then whenever we have to call DFS from a new connected component, we increment that counter. So all of these vertices get marked with label 2, they're in the second connected component, and these ones get marked with label 3. So if we're given 2 vertices, we can use DFS to find, is it even possible? Is there even such a path between 2 vertices? So if I had some vertex here and another vertex here, I can check which connected component do they belong to. Do they belong to the same one or not? If they belong to different connected components, then there is no path that connects them. Otherwise, they belong to the same connected component because there would be a way to reach them. So we can pretty quickly determine, is there such a path, by labeling those connected components. But suppose we knew that there was a path. Now we want to find what is a path that connects them. So this is what our pathfinding algorithm uses. So we're essentially going to, in our DFS, we've labeled edges as discovery edges or back edges. We're effectively going to follow which discovery edges did we use starting from our original vertex. So we want to find a path from vertex A to vertex F, and we ran DFS on A. We're going to follow which discovery edges did we use to get to F, just kind of following those discovery edges back from our starting point A. So how we're going to do that, we can keep track of a stack of which vertices and edges we followed in order to get to whatever vertex we're currently at. And if we finally found the vertex we're looking for, we want to figure out a path to some vertex, let's say F, then we're going to print out all the vertices and edges we followed to get there. If we took some other kind of detour before we got here, then as we work our way back through the recursion stack, we don't want to keep track of that detour. So for example, here's our stack S, and let's say we start at vertex A and we want to find a path to vertex F. So I'm going to label each edge just based on in what order we would encounter it along a DFS traversal. And here's 6. Okay, so our stack, well, note that in the algorithm that I have here, everything in red is the same as what you've seen before in our DFS algorithm. What I have in blue are just those modifications that we would need to make so that we can keep track of this path as we find it. So initially, again, we mark every vertex and edge as unexplored. We call then path DFS from our starting vertex, which in this case is A. And we're going to just follow DFS as we know it. So we're going to mark vertices and edges as being, vertices will be visited, edges will be marked as back edges or discovery edges. but with the addition that we're only going to keep track of those vertices and edges which led us to the vertex that we want to find a path to. So initially we're going to add our starting vertex A, and we're going to keep checking if at any given point in time we found the vertex we're looking for, F, then we're going to stop there and return everything that we have on the stack. At that point, our stack will include all that sequence of vertices and edges we followed it from our starting vertex to get to this ending vertex. But until we reach that, we need to continue traversing through our graph until we find that vertex. So we'll follow, let's say, edge 1 to get to vertex B. So as we follow edge 1, we're going to put that on our stack. Then we call DFS on B. And then we follow edge 2 to get to C. We call DFS on C. We follow edge 3 to get to D, and then edge 4 to get to E. Now at this point, we're going to backtrack because we still haven't found the vertex we're looking for, but we have nowhere else to go from E, no other incident edges that haven't been marked. So this is why we're going to pop items off the stack. So when we're finished with this path DFS call on vertex E, vertex E has no other incident edges, so we're going to pop it off the stack. So this is our return from that recursive call on vertex E, and so we're going to pop the edge off the stack that we used to get there as well. Now that we've finished, there are no other incident edges from D that we can explore. We already explored this one and we got here from this edge. And we still haven't encountered that vertex F we're looking for. We're going to pop the vertex and edge off the stack. And now from C, we have another edge that we could follow. Either this edge to go back to vertex A, which we already had a way to get back there, so we don't need to follow that one, or this discovery edge, which leads to F. So we're going to add now 5 and F onto our stack. Now at this point, we call path DFS on F, and we realize, we have finally ended at, that was that vertex that we wanted to end at, and this gives us the path to get there. So we go from A through 1 to B, through 2 to C, through edge 5 to get to F. So we can find a path between two vertices in total linear time. This is just the cost of DFS. And we had a few extra operations that we performed, but those operations that we added, this is within one path DFS call, which we end up calling path DFS a few times. But within one call, we have only constant time operations that we added, pushing or popping off of a stack. And when we're finished, we can even end early once we find that vertex we're looking for, and we return that entire path. Now it's important to note here that DFS will find a path between vertices, but this isn't guaranteed to be a shortest path. Note that we could have followed the path from A through edge 6 to get to vertex C, and then through edge 5 to get to F. So this would have only used 2 edges. This is shorter than the path that we found, which used 3 edges from A to B, and then C, and then F. But this will always give us a path. If there's a path, we'll be able to find it using DFS. Now, we can use a similar approach in order to find a cycle in our graph. Now, if there is a back edge, if throughout our DFS traversal we encountered a back edge, then there's a cycle in our graph. So if we just want to check yes or no, is there a cycle, the existence of a back edge means that there is definitely a cycle in our graph. But if we actually want to find what that cycle is, we can, kind of how we did with finding a path between vertices, use, starting from this back edge, which discovery edges did we follow in order to reach that point until we find a common ancestor vertex. So again, I have here in red those same, this is just what we have for our regular DFS algorithm. And then in blue, I have those additions of how we're changing this in order to make this find a cycle. So we want to find a simple cycle. And we're going to again keep track of a stack of what vertices and edges we followed in order to encounter some cycle. So let's say we start at vertex A. We want to eventually find this cycle C, D, E, F. But let's just suppose we started at vertex A. So we'll add And let me label edges in the order that we would encounter them as well, so we can keep track of those. So we'll add A to our stack, and then just following DFS, we'll add vertices and edges as we encounter them. So we'll add 1 and then B, and then when we call cycle DFS on B, we'll add 2 and then C. And then from here we have a few choices. We don't know yet that we have a cycle, so we're going to wait until we encounter a back edge. So we'll follow this edge from C to D and keep track of how we got there. We'll follow the edge 4 from D to E, the edge 5 from E to F, and then it is at this point in time that we know, we have a cycle. This is that back edge from F to C. So as soon as we find a back edge, we know there is a cycle, and we're going to follow all of those discovery edges that we used to encounter it until we come back to this common vertex. So we're going to work our way back through our stack and only keep track of the part of our stack which is this cycle. We don't need the beginning part which doesn't consist of our cycle. Okay, so we keep track of, here is that back edge E. W, or in this case C, was the vertex that it's leading towards. And we're going to repeatedly pop items off of our stack until we get back to that vertex W. So we're going to pop all of these items off of our stack until we get back to vertex C, because this was the only portion of our cycle that we wanted to keep, right? We didn't need the beginning path here. This wasn't contributing to our cycle. So at that point now we can return, here was that cycle in our graph. It consists of the following vertices and edges. Oops, here's edge C coming back to vertex C. So this was our starting point of our cycle. We followed these discovery edges until we reached this back edge, which led back to the same vertex. So this is a pretty quick way that we can find a cycle in our graph using depth first search.